And welcome back, AP Physics 1 students. Let's pick up right where we left off. We just finished problem number 6, and so in our packet we're going to turn to problem number 7, where we continue our saga on the frictionless ice rink. Now we're going to talk about some collisions. And so we'll define collision as when objects start apart and then bump into each other. Sort of the reverse of an explosion, where the objects started together and push each other apart. Now they're starting away from each other and they're going to collide. They're going to bump into each other. So take a second to write that down, or you can put it in your notes, whether so the notes are on the problem set, wherever you're going to find it. All right, so go ahead and read problem number 7, and we'll do it together. Make sure you pause the video. Okay, so here's a little bit different, right? They're not starting together. We got little brother coming in, chaperone son's just standing there, and before anything we want to draw the picture. So draw a representation of what happens, where we see that little brother rebounds. You think, what does that mean? Well, it means he was coming into the left, and he's going to rebound to the right. And of course, as a result, chaperone's son is going to move off to the left, so it might look something like this. I've taken the liberty of already assigning to the left as positive, which seems to make sense, considering chaperone's son is coming into the left. So I might as well call that the positive, although certainly you can call it to the right positive if you'd like to. You can always call whatever direction positive makes more sense to you. Okay, so pause the video, do the conservation of momentum part, and then we'll come back together to talk about the other parts of it. Okay, so this system does start with momentum because little brother is coming in at 10 meters per second, and notice I'm using the positive sign there because we're calling left positive. In the after situation, well, he rebounds to the right, and since we call left positive, and now he rebounds with a velocity of negative 2.5 meters per second, we leave v2 prime as the unknown. That's going to be the velocity of chaperone's son because he's m2, and we should be getting positive 7.5 meters per second. Of course, in your problem set, it says to the left, because I really don't know what you're going to call positive. I just think left is a convenient positive direction. Okay, but the rest of it now says now we're going to add in the kinetic energy component. So we're going to find the total kinetic energy in the system beforehand and afterwards. So then you think to yourself, okay, kinetic energy, what's the equation there? Well, it's 1/2 mv squared, which, hey, that's a little bit like momentum, so I want to make sure we're careful about that. Kinetic energy, 1/2 mv squared, momentum, just mv. And we want to remind ourselves that energy is a scalar. And so we want to find the kinetic energy in the system. Well, all we do is we find the kinetic energy of object 1, and then the kinetic energy of object 2, and since everything is scalar, just add them together. And so in the starting situation, go ahead and prove it to yourself that kinetic energy of the little brother is 1500 joules, and the kinetic energy of the chaperone's son, of course, is 0. Just pause the video, make sure you can calculate that and get those kinetic energies. To find total kinetic energy, all you do is add them up, and so the total kinetic energy in the system to start off with is just the 1500 joules. Go ahead and do the same thing for the after situation, keeping in mind, again, kinetic energy is scalar. And so here we should be getting kinetic energy 1 for little brother is 93.8 joules. It does not matter that it's going to the right because it is scalar. Even if you were to try to put in the negative 2.5 meters per second, when you square it, you'll still end up with a positive amount. But it doesn't matter because everything's scalar. There shouldn't be any signs on it. And there's no such thing as negative kinetic energy. Just the fact that he's moving, he has kinetic energy. For chaperone's son, he's got 1410 joules for a total kinetic energy in the system of 1500 joules when you round it to 3 sig figs. So what's interesting about this? Well, this is typical of one particular type of collision. So going back into your notes, we're going to detail the types of collisions. This first type is called elastic, where the objects bounce off, where they separate away from each other in the after situation, and the total kinetic energy is conserved. This is a very rare kind of collision. In the real world, it doesn't happen very often. It's only really contrived examples, such as this one we're looking at with the frictionless ice. Can kinetic energy be conserved? But sometimes at the microscopic level, you'll see particles undergo elastic collisions, so it's very useful to talk about there. All right, so let's go on to problem 8. So here's the setup. Go ahead and read it, draw the picture, assign a positive direction, do the conservation of momentum, and then do the total kinetic energy both before and after. Pause the video, try it all on your own. Okay, so here's my picture for afterwards. It says that little chaperone's son comes to rest, so in that situation he's not going anywhere, and physics bully moves off. So physics bully being the villain of the story. There's always one in the crowd, someone who doesn't really want to go on the trip, someone who refuses to believe that the ice is purely frictionless. He's the physics bully. So he gets bumped by chaperone's son. The physics bully goes off with v1 prime since he's m1. I'm going to call it left positive, considering everything is pointing to the left anyway. Here's my conservation of momentum and the energy results. We should have no problem getting the positive 3.75 meters per second for physics bully. In the before situation, only chaperone's son is moving, and so he has all the kinetic energy, which, by the way, is the exact same kinetic energy he had in the previous problem, so if you didn't want to recalculate it, you didn't have to. In the after situation, it's just physics bully that's moving, so he's got all the kinetic energy of 703 joules, and we compare. And so you see, well, look, the total kinetic energy to begin with is 1410, afterwards 703. Was kinetic energy conserved? And of course the answer is no. So now we have an inelastic collision. We define that as being a situation where objects bounce off, still they separate, but in this case kinetic energy is not conserved. This is much more typical in the real world. This happens all the time. So we say to ourselves, well, where does the energy go? By conservation of energy, you can't just lose energy, it's got to go somewhere. So take a second to think about that. When objects collide, what sorts of energy are produced? Hopefully you come to the conclusion that when objects collide, heat energy is being produced. As they collide, the particles vibrate a little bit more, they're set into motion, and that transfer of energy is known as heat. Also, of course, sound is being produced. When objects hit, they make a sound, and sound is one of our non-mechanical forms of energy, taking mechanical energy out of the system. Alright, let's go ahead to problem 9. Go ahead and read it, draw the picture, set a positive direction, and solve using conservation of momentum and for the energy of the system before and after. So physics bully is not taking this lying down. He does what bullies do. He comes back around, and he picks up chaperone's son. Now, here I didn't draw the picture because the picture I would try to draw using my crude drawing tools on PowerPoint weren't going to really cut it, but hopefully you do something fun. I look forward to seeing your pictures. Usually I like your little stick figure theater. You can see some interesting results when we come back together. But I'm going to call it to the right positive, considering physics bully is moving to the right. The conservation of momentum equation changes just a little bit because now the objects combine. So the way we show that is by saying m1 plus m2. The mass is combined to a single mass, and there isn't v1 prime or v2 prime. They have a single combined velocity. We're just going to call that v prime. Put our numbers in, and we should be getting positive 2.5 meters per second, which correlates to 2.5 meters per second to the right, which makes sense, right? The physics bully comes in with all the momentum. Chaperone's son is just standing there, and then momentum is shared by the two because they have a combined mass. The kinetic energy in the system is exactly what physics bully had before. So again, if you didn't want to calculate it, just use the results from problem 8, which is 703 joules. And when you go ahead and use the combined kinetic energy with their combined mass and their combined speed, we get 469 joules. And so, is kinetic energy conserved? Clearly it's not. However, this is a third special type of collision. This is what we call a perfectly inelastic collision. It's as inelastic as it comes. In this case, the objects do not bounce off. The objects combine. They move off as a single object. But again, total kinetic energy is not conserved. And so these last three problems are typical of the three main types of collisions that we see. No matter what, momentum is conserved, but kinetic energy is only conserved in this elastic collision. The problem would have to tell you it's elastic, or you'd have to go through the problem and actually calculate the kinetic energies before and after and see whether or not they match. If they don't, it's just some form of inelastic collision. And of course, the perfectly inelastic is the easiest one to identify because the objects combine. So as soon as you see that, you know automatically kinetic energy will not be conserved. So hopefully you took good notes and you were following along with the problems. I hope that you were not just watching the solution on screen and then writing down the answers. That's not going to help you. And if that is what you were doing, please go back and solve the problems yourself because that's the only way you're going to learn this the best way for you to have success. So when you come back into class, I'm expecting that you can identify the types of collisions. You can do these conservation of momentum problems with ease because we're going to take it to the next level when we come back together. Certainly we will also be doing some demonstrations so you can visualize the different types of collisions and explosions, but you have to have done the problems on your own to have success.